talk will be focusing on this whole paper. If you want to read it, you can read paper number 2. The whole talk is about heuristic extrapolation with restart. The idea is that if you solve an optimization problem, you just extrapolate in all the steps. That gives you some benefit, because if the extrapolation is doing good, you gain speed up. But if you do a wrong extrapolation, then you do some safeguard, that is restart. And the whole idea is to make this restarts cost nothing. Then you gain pure speed up. So what's the problem? Non-negative canonical polyadic decomposition, also called tensor factorization. So this is the problem form. You have given data T that is a volumetric data. For example, for order 3 tensor, it looks like a cube. And your goal is to find factors that fit this data. So the statement is try to accelerate the algorithm solving this kind of problem. So for example, let's consider we only have 3 variables, that is u, v, w, and you want to find u, v, w by minimizing this function. You solve this problem by minimizing the problem on u, fix v and w. After that, you solve the subproblem on v, you fix u and w. Lastly, you solve the subproblem on w, and you fix u and v. And you repeat the whole thing. This is block coordinate design. And this is the algorithm. In the block coordinate design update, you don't really care how you perform step 3, 4, 5. This subproblem admin is an optimization problem itself, and you can use whatever optimization algorithm you want, or you can solve this problem inexactly. So what we propose is we add extrapolation. First, we have the extrapolation variable, that is the auxiliary variable labeled in red. And then whenever you do extrapolation, you do in this form. You have a variable u, and then you have the previous variable, that is the variable in the previous step, or you can call it the history term. And this is basically the momentum, and this beta is basically the weight of how much momentum you add on this variable, or you can call it the extrapolation step size. Beta is basically a parameter. So in this case, the scheme is basically you update, you extrapolate, you update, you extrapolate, and so on. The number 3 to number 8, these all lines are the same for many extrapolated algorithm for convex problem and non-convex problem. The difference is how do you choose to solve the mean of this problem. Here, this is a heuristic. That means there is no theory. Here is the heuristic part. Because you do extrapolation, you don't know is doing the extrapolation good, because it's possible the extrapolation is actually bad. That's why you need safeguard. The safeguard is here. So basically, this is called restart. It means what? You just check, is the extrapolation good? If the extrapolation is doing good job, that is the error go down, then you keep the extrapolated value, that is you replace this value by the extrapolated value and so on. And then you do some tuning. I will explain this later. But here, for the first if condition, it means if the error goes up, then you restart. That means you abandon the extrapolation. You say, oh, this line is bullshit, this line is bullshit, this line is bullshit. I just keep those UVW, because the UVW are obtained by upmean of the F, so they are guaranteed always go down. So by doing so, you can guarantee it always go down. And if restart didn't occur, that means here, then you gain the speed up by extrapolation. In the following 1 or 2 minutes, I will just keep showing you this works for many problems. For example, to accelerate the algorithm for solving non-negative matrix factorization, that is, the W has to be all non-negative and H has to be all non-negative, and you want to find W and H such that they are equal to X. So this is an experiment showing that the extrapolated method works very well. For example, these 2 curves are the unextrapolated method. One is using ANLS, which is active set. Another one is called AHLS, which is using block coordinate descent algorithm. So the unaccelerated method converges like this, slow. And all the curve here have extrapolation, that is by the herd, that is the heuristic extrapolation will start. And typically this line is an algorithm with theoretical convergence guarantee. Basically, this is the accelerated alternating proximal gradient. And you can see this figure just to show that this method is not as good as the herd. Now it works also on tensor. And this is showing the convergence of the objective function. You can see that this is in terms of iterate, this is in terms of time. You can see it works for iterate and time and in many order. And notice that here, this is showing that the way I choose to solve this upmin, I'm using AHRS, it works. And if I switch all the sub-block update to ADMM solver, it also works. Actually, it works better here. And actually, it works for whatever BCD. You can replace ADMM, AHRS by gradient descent, MUAS, whatever. It all have this kind of behavior. And this table is just showing that this behavior keeps appearing for many different test cases. For small cases, highly ill-posted cases, unbalanced size, to noisy, to real data, to big data. For example, this data is a 10 to the power 9, which is you cannot load it into a CPU. This is the smallest big data. So this means that this method also scalable. And this slide just show that this also works with a Tucker form. That is, here you don't have an I, but you have a G. And this is just to show you it works for the data. This is the big data, video data with very bad yield condition number. That's why the blue curve or the purple curve, you see they almost does not go down. And this is to show that it works for CPD. That is, you don't have non-negativity constraint. Just one point, because this problem you don't have constraint, actually you can say, oh, I solved this problem, take the gradient and set it to 0. Then this update is called ARS, alternating least square. And this update is also the Newton's iteration. So it means that this method also works for second order method. And then lastly, this is a very new result. It also works for complex number. That is, instead of fitting W and H, you also want to fit a matrix D, DE. D is in complex matrix with a specific constraint. This is just for the machine learning purpose, but it shows that it also works very well. This is on speech data, that is some voice, and then you want to decompose it. And because this is a complex number, so you need to use a complex number formulation called Rittinger flow, and you can see that it has very good performance. And this is the algorithm, but I will skip it. I will just talk about the most important part, why it works so well. The idea is very simple. As I said, you always perform extrapolation. Because this is heuristic, that means you tune the extrapolation weight, and numerically, you don't know does it work. It's possible the error will be better. That is, the extrapolation is doing good job. That is the green block here. And it is also possible it's doing bad job, is going up. So the idea is very simple. If it's doing good job, then you keep going and you tune the parameter, you make it bigger so that in the next step, it extrapolate more. You become more ambitious on the extrapolation, or you add more momentum in the next step, because you are thinking, okay, you are now in this landscape. So in the next step, you can push more. But if the error increase or the fitting cost increase, that means you are in this kind of landscape. Okay, you should think of it in 3D, it's not 2D, because it means that in this direction it's going up, but actually you can go down by the other direction. But the idea is very simple. If the error is going up, you want to do something called restart. That is, you reject this extrapolation, you go back to this point. Because you are doing a bad extrapolation, that means your extrapolation parameter is a wrongly chosen number. So in the next iterate, you want to tune this number to a better number. So what makes extrapolation doing bad? The idea is very simple. The extrapolation weight is too big. Then how to fix this problem? You just tune down the extrapolation parameter. That is, in the next iterate, you divide your current extrapolation parameter by number eta larger than 1, then this will go down. And then there are also other parameter, gamma, beta bar. I don't have time to explain, but this is the idea. So there are some important points why there's no theory, no converse, and why it works. I don't have time to explain, but I just want to explain one important thing, why this method works well also in terms of time. The goal of doing extrapolation is we want to have faster convergence, but the drawback of doing extrapolation is that it's possible you are doing a wrong push. Then if you are doing wrong push, that means the computation on doing the push is wasted. And also to check whether you're doing a good push or wrong push, you need to compute the restart criterion. This can be expensive. But why in this car plot you can see that it have the same behavior in terms of time and iteration is because the restart cost is 0. That is, you don't have losses in the computational time when the restart is occurring. It's because to do the checking of the extrapolation is doing good or bad, we are computing the criterion function f hat that is not f but slightly perturbed version of hat, and we can show that this surrogate criterion for approximating the cost function f, which is used as the restart criterion, will converge to the true value as the iteration proceeds, and this gives the cheap computation because this f hat is computed by reusing the already computed component in all the previous update. So now it's time to stop. So this is the one-line summary I presented in the beginning. So now you understand what it means. Heuristic, because there's no proof. I didn't explain why there's no proof, but there's some theoretical thing. Extrapolation is in this form, which is Anderson or Nesteroff, and it is a block-running design. You can do it block by block in exact or inexact BCD manner with reduced the restart cost because we use the f hat, which you don't have computational burden, and then this works very fast on whatever factorization. So that's the end.
Okay, great. Thanks a lot, Anderson. So let's see if there are questions for Anderson.
Yes, I have a question. So the surrogate function, how general is that? That is it one has to really come up with the correct surrogate functions for each different problem?
I don't have time to talk about it, but here's the thing. Let me go to a very specific. Okay, let's say you have 3 block U, V, W. The original restart scheme is you compute the cost value at every iteration. That means you compute this guy. But the thing is, after you do this update, W changes. So if you really compute this guy, you have to compute all the terms inside from scratch again. Because whenever you finish the update, their product in this expression will change. So here's the idea. If you look closely, the f hat, the surrogate, actually is computed using the u hat, v hat, and wk. So what is u hat? U hat is here. This is the extrapolated variable after the update of u. After this line, you doing the line here, this variable won't change. Same for the v hat. So the term related to u hat and v hat will stay the same. And after this line, w change. So you have the component for computing this guy related to w. So you compute the surrogate actually using the extrapolated sequence for the previous block, but not for the last block. That means the last block is using the original sequence. It gives you a more accurate surrogate. But if you use the W hat here, it also works. This is more completed illustration. Now you have n block. So you have A1, A2, A3 up to AN. And you can see the F hat, the surrogate. You are using A hat 1, A hat 2 up to A hat n minus 1. That means all the previous block except the last block, you use the extrapolated one. And this one is the most recently updated one. And this is the surrogate. And all the terms you need to compute for computing this function f is already computed in the previous step. So doing this line asymptotically, it costs nothing. That's why you always gain pure speed up by doing extrapolation.